Yes.
Yesterday in a tutorial, we had a discussion about diverging energy densities. Is there a physical meaning to those?
Yeah, so density of states is basically number of states that are available for occupation given energy. If this diverges, that would have very important consequence for experiments in the sense that the response of the system will be dominated by those states. So what that means is, say you measure specific heat, conductance, or some physical observable as a function of energy. You might get a large response if there was a density of state in, for example, if it's an electronic property, if the electronic density of state diverges, then you will get a large response. Now, keep in mind, we will have some examples later in the course where we will see this. Keep in mind that for the moment you have calculated electronic density of states, even in this example, but you ignored a lot of things. You ignored electron-electron interactions. You ignored electron-ion interactions, which we'll see later on, maybe tomorrow or day after that. It will give rise to electron-phonon interactions. And all these interactions would change the band structure itself also. And so essentially, I would say the key point, experimentally, when you measure some physical observable, usually you will have no divergences. And a lot of effort goes on in understanding what is really giving it a finite, what is really giving us a finite answer. So in some cases, you want to understand what is giving the state of electrons a finite lifetime, for example. And typically, we find these answers to be related to electron-electron interactions or electron-phonon interactions. Any other questions? So yesterday, we started with the Hubbard model, which is the kinetic energy single particle terms in the Hamiltonian and the two particle terms, assuming that the momentum dependence of the interaction potential, there is no momentum dependence. So the interaction potential is constant. So in real space, this corresponds to having a point-like interaction. So the delta function in real space, constant in momentum space. And now we assume that the expectation value of C dagger C operator takes this form. This is our assumption. So we assume that the ground state of the system, if you destroy a particle with some momentum, you should create it with the same momentum. And if you destroy a particle with some spin, you should create it with the same spin to have a non-zero expectation value. And we use this definition. We put it back in the Hamiltonian, and we can show that the interaction term, that is this term, if we go through all the steps of mean field theory, it can be written like this. Crucial aspect is if we pair these two guys, if you define the deviation operator using these two operators, you see the spin label is same here. And in the Hartree term, you would see that the spin labels are same for the operators. But if I anti-commute this and these two, if I anti-commute these two and then define the deviation operator, you would see that these spin indices are not going to be same, and this gives rise to some delta functions. All this can be nicely rewritten in this form. So now we are going to look at this equation and see what this really implies. So let's look at what this interaction term is, or let's just focus at the let's look at this first term. Now this involves some more product of expectation values and square of some expectation value. We'll keep this for the moment, but we are only looking at the operator part of this equation. set sigma equal to 1. So for sigma, or let's set sigma equal to up spin. So when sigma is up, what does this term contribute? So for sigma equal to up, the first term simply gives you u sum over k and down ck up dagger ck up. Let's see how. So sigma is set to up, so this is up, and delta function contributes only when sigma prime is equal to up. But this term, sigma prime, there is no delta function, so you get n up plus n down from this term because you have sum over sigma prime. So you have n up plus n down coming from this term, but this term will give you minus n up. So as a result, when you do the sum over both sigma and sigma prime, you will end up with n down ck up dagger ck up. Similarly, for sigma equal to down, the first term will be u sum over k and up ck down dagger ck down. The reason you get the kinetic energy or the single, now the quasi-particles for upspin have energy depending on the density of the downspin particles is because of these delta functions, which are there because of the Fock term. So the Fock term in the interaction potential gives rise to this special feature where the occupation of upspin has a prefactor that is density of downspin particles, and occupation of downspin depends on the density of upspin particles. So now I can write down the mean field Hamiltonian. This is sum over k sigma. Now I can combine all of the terms. So now I have only single particle terms. So I can redefine, so I can include the self energy and redefine the dispersion relation as this. So this mean field energy is the original dispersion that you have and this terms. So we've seen that so far these spin densities, they appear in an unusual fashion in this mean field Hamiltonian. Next, what we are going to do is we are going to use this Hamiltonian to calculate this expectation value, and thereby we'll arrive at the self-consistency criteria. Now, what is our goal? Our goal is to find out when interaction strength, for what values of interaction strength the system can support a ferromagnetic state. So really interested in understanding when does a system become a ferromagnet. So we are going to impose the self-consistency criteria, and that will answer our question. So what do we want to do? We want to calculate the spin density n sigma, which is 1 over omega sum over k and k sigma. Now this is expectation value of the number operator. So this expectation value we are calculating using the mean field Hamiltonian now. So this, what I'm going to do next is a trick or something that you would see a lot of times in condensed matter. So when you have an expectation value of number operator, you can use, if it is a fermionic system, you can replace this by the Fermi-Dirac statistics, or if it's a bosonic, if they represent bosonic operators, you can replace them by Bose-Einstein statistics. What that really means, you are summing over all momentum of the expectation value of the number operator. So at t equal to 0, at 0 temperature, this expectation value for fermionic operators is going to be 1 if the state is occupied, 0 if it is unoccupied, and that is precisely the Fermi-Dirac statistics. So you can generalize this to higher temperatures by defining something which is called chemical potential. So let me just write down the expression once. So here beta is inverse temperature, 1 over Boltzmann constant times the temperature. This is the mean field energies, and this mu is now the chemical potential. And this chemical potential is generalization of Fermi energy. Let me define it this way. At t equal to 0, at absolute 0, chemical potential is equal to Fermi energy. So all states below the chemical potential at 0 temperature are occupied. All states above it in energy are empty. Let's assume that this dispersion here is parabolic to make the calculation simple. But now you know that this can also be some particular band, and this band can have some complicated dispersion. But in this course, in this lecture, we'll consider a parabolic dispersion. Now, this is a formula written for general temperature, but again, we'll simplify the calculation and we'll set the temperature to 0. At 0 temperature, this can be simply replaced by the theta function. Okay, I've assumed one more thing, so let me do it in one more step. So now I'm going to calculate n up, and I'm going to calculate n up at t equal to 0, and this I can write as theta function Any questions? So my goal is to calculate an spin up density and spin down density and see if they're different. And if they are different, we have a ferromagnetic state. Yes.
Why is it equal to the theta function?
So I set temperature to 0. So all states below Kf, Fermi momentum and Fermi energy are occupied. All states above are empty. So what is this occupation number? So this simply gives 1 if this K represents a state that is occupied otherwise, and this mu is defined, mu at t equals 0 is Fermi energy, so that this quantity being 1 only if the state is occupied. Now this is a very easy integral. Actually, the integrand is just 1. So all we have to do is convert this sum to an integral. So this is an integral in momentum space of the theta function. Now, notice that this integral is symmetric in the sense that this is a 3-dimensional integral. You integrate over k, the polar angle and the azimuthal angle in momentum space. The integrand is independent of that, so that part is easy. You just have an integral over the momentum, k, and that will give you a finite. So the integrand is 1 only if k is less than kf. So assume you have a Fermi sphere. If the radius of this sphere is less than kf, then theta function gives you 1. If it's more than kf, it gives you 0. But now the crucial thing is that kf is not same for upspin and downspin. Now in the tutorial, you did a problem where the Fermi wave vector, kf, was different for upspin and downspin. And if you remember why that was the case, it was because you applied a magnetic field. So in the presence of magnetic field, Fermi vectors for up and down spins can be different. Here, keep in mind there is no magnetic field. And this is happening, kf up and kf down are different because you have ferromagnetic state. So there is no magnetic field, still the Fermi wave vector for upspin and downspin can be different. So I can write down this integral as integral from 0 to kf up. So I'm calculating expectation value for upspin. So I will integrate for the Fermi wave vector for upspin and just dk over 2 pi square k square. So this is simply kf up cube divided by 6 pi square. How is this kf up defined? This kf up is defined such that this quantity is 0, the theta function, so that all momentum below kf up are occupied. So kf up is defined And we have the equation mu minus h bar square kf up square over 2m minus u n down is equal to 0. Yes.
Will there be a vector of 2? But when you do the angular integral, you get 4 pi.
Oh, yes, you get 4 pi, and this is 8, so there is 2, and this is k. Oh, I took
2 pi all squared. Sorry.
Yeah. If there are some factors, please spot it. There could be some errors, but the details of calculations are in the notes, which I assume you already have. So the key idea is, again, that spin density for up spin electrons, you integrate over Fermi wave vector for up spin. It is defined using this equation. And now the key point to remember is there is no magnetic field, and still you have different Fermi momentum for upspin and downspin. So you can do similar calculation for the downspin, and you will find that the down density, spin down density, is kf down cube over 6 pi square, and where kf down is defined as mu minus h bar square kf down square over 2m minus u. Now you have spin up density equal to 0. So essentially, I'll summarize what we have really done. So we saw earlier when we defined Fermi wave vectors, you can always write this wave vector in terms of electron density. Now we have included spin, and because of Fock term, the Fermi wave vector for up and down spin are now different. They are written in terms of up wave vector for up density, down wave vector for down density, and these two are now different, and they are given by these two equations. This includes, so when you have kf up, you will have un down, and when you will have kf down, you'll have un up. So where is this coming from? This is coming from imposing the self-consistency criteria. So we can write down these two equations, and let's try to solve them. So our goal now is to solve these two equations to see what solutions correspond to upspin density not being equal to downspin density. So you can subtract these two equations, and what you will get is next I'm going to define some new variables to take care of all these redundant factors. So I'm going to define a quantity which we'll call spin polarization. So spin polarization, let's call it zeta. This is defined as n up minus n down divided by n up plus n down. And we'll define an effective interaction strength gamma as 2mu h bar square So now we have defined this interaction strength. Not only it includes U, but it also includes total electronic density. That is n up plus n down. In terms of these two variables, you can recast this equation by looking at, now zeta is n up minus n down over n up plus n down. That implies you can think of 1 plus zeta. This, you can show that this is equal to 2n up over n up plus down. And similarly, you can do 1 minus zeta. This will be 2n down over n up plus n down. And putting all this back, you can eventually show after a few steps of algebra that 1 plus zeta to the power 2 by 3 minus 1 minus zeta to the power 2 by 3 is gamma times zeta. So this is same as this equation here, rewritten now in terms of spin polarization and interaction strength, which are defined here. So what was our original question? For what values of interaction strength we have a ferromagnetic state? So now we can address that question by solving this self-consistency equation. Now this equation has three types of solutions. If gamma is less than 4 by 3, the only solution is zeta equal to 0. This implies that the up density is same as down density. The second type of solution is when gamma is between 4 by 3 and 2 to the power 2 by 3. This implies that the spin polarization zeta is between 0 and 1. And the third case is when you can, this is very easy to verify, simply put gamma equal to 2 to the power 2 by 3 in this equation, and you would see that the spin polarization must be equal to 1. So this self-consistency equation has 3 types of solutions for interaction strength small, that is weak interactions. You see, you get no spin polarization. So the system remains isotropic. The density of upspin electrons is same as the density of downspin electrons. If you have intermediate value of interaction strength, which is given by this, then you see that there is some spin polarization. So the upspin density is no longer equal to downspin density. And this we call as partial polarization. You can also call it as weak ferromagnetism. And then the third solution, when gamma is equal to 2 to the power 2 by 3, then you find that this spin polarization must be equal to 1. Now this is full polarization, or also called strong ferromagnet. Now, once you've already fully polarized the system, if interaction strength is even larger, you will still have a strong ferromagnet. Yes?
There are no solutions for gamma greater than 2 to the 2.
So for gamma greater than 2 by 3, this equation does not permit. So at gamma, so we stop at interaction strengths equal to 2 by 3, and then look at what does this critical point really means, and we see that this corresponds to full polarization. And then once you have already have full polarization, if you increase, you can think of like this equation has or the solutions have a branch cut, in the sense that once you have already polarized the system fully, there is nothing more left to do. So the interactions have already fully polarized the system. Yes?
Sorry, I don't understand how, because you're saying this is a self-consistency equation, I don't know how to see it directly, because we just did some stuff.
So to see directly is just to look at this. So we now calculate the expectation value using the mean field Hamiltonian. And this is the definition, or this is the criteria for self-consistency. First, we just assumed something, right, for these expectation values. And now we are really calculating them. We assume something, we calculate the Hamiltonian, and then we use this Hamiltonian to calculate the expectation values again. And eventually, so now these values, these are the self-consistent solutions. Well, now we still have to figure out what these expectation values are. And once you put these self-consistent solution in the Hamiltonian, you will have your mean field Hamiltonian. Yes?
I have 2 questions.
Yes.
The first one is, so you got those 2 extra terms in the Hamiltonian, right, which depend on n sigma.
Mm-hmm.
Did you absorb them to the chemical potential, or where did they go?
I had them when I wrote down n sigma, and then at this step, I'm only looking at n up. So for n up, the only term that survives is un down. So if you look at the top of the line, the first term only gives you n down for sigma. So I'm now restricting it to calculating up and down spin densities. independently or separately. And the second question?
Okay, I'm not sure about the test. Okay, anyway. It's just interpretation. So gamma is basically the interaction strength over some energy scale, right?
Yes.
So what's the physical interpretation of this other energy scale?
So U is the interaction strength we started with. What we're really doing is multiplying it with total electronic density. So now this corresponds to interaction strength, which includes the fact that this density can be large or small. So if the electron density itself is large, this interaction strength is large, and so on. So what it physically means is it includes the effect of total electron density.
Okay, so it basically compares U with the Fermi energy.
Yeah. So maybe I misunderstood your first question. If you want to take time to rephrase it, I'm sure it will be of value to everybody.
Oh, I was just wondering, so you would expect in the Fermi-Dirac distribution to have the total energy of the system, right?
Yes.
And you subtract.
Maybe you're asking about these two terms. Sorry. Okay. Sorry, I misunderstood your question. So these two terms, if you look at, for example, up and down spin, you will see. So you can ignore them for the moment, or when you put back, you will see. Let's say we absorb them in chemical potential or Fermi energy. I think that's what you answered to begin. Yeah. So you're right. We can absorb them in the chemical potential. Any other question? So there is another way to visualize this ferromagnetic state, and that is what we are going to do next. So this first class of solutions, so this is a plot that you would see many times. So we're going to discuss this. What we are going to plot is, we're going to plot density of states on x-axis and energy on y-axis. And these are the first type of solutions. And we are going to make two plots, one for upspin and one for downspin. Yes?
Sorry, I just have a question. Does this analysis need to work at finite temperature?
So you can generalize everything to finite temperature. And if you do that, you can also calculate the transition temperature. And so there are many ways of doing mean field theory. And if we have time, we can discuss that later on in the course. But you will find what is called Curie temperature, below which the system becomes ferromagnet. So we are going to plot is density of states on x-axis, energy on y. Now in the tutorial, you calculated density of states in 3 dimensions for electrons, and you showed that this goes as square root of E. So we are going to plot this here. This is how this plot will look like. So this is square root of E. So the first solution, and now I'm going to draw a line corresponding to the chemical potential or Fermi energy. Now rho E, this is density of states. Rho E multiplied by dE gives you the total number of states between energy E and dE. So this area between this curve here, this area gives you for upspin. So this is now plot for upspin. This area gives you the upspin density. Similarly, this area, this gives you, so this is a plot for downspin. This gives you the downspin density. So the first type of solutions correspond to a situation where the density of states is such that the total spin density, so it corresponds to a situation like this. Now I've drawn square root of E. In general, you will have bands, you can have very complicated function. The density of states can be a very complicated function. So we'll draw density of states and then look at the Fermi energy, calculate the upspin density, downspin density, see if they are equal or not. The second case, this corresponds to a situation when the upspin density is like this and the downspin density is this. This is the Fermi energy. So now you can see that N up is much larger than N down. Right? So again, these are for free electron gas, density of states for free electron gas. In general, you can have a very complicated function and you'll have to do this, you'll have to calculate this area accordingly. And then the third case, for gamma equal to 2 by 3, you'll get a situation where this curve is just above this, and for interaction strength larger than that, you will have this further up. But as you can see, that does not really make a difference. For the third type of solutions, you only have one type of electrons in the system, either up or down. Yes.
Why did we plot the energy as a function of density of states instead of the inverse?
This was not my first choice. This is the convention. I did not choose this. But it's the only reason I show this is because it's heavily used in condensed matter. So you should know that such plots exist. Now, sorry. There is another way to physically understand why we have this ferromagnetic solution. And next, I'm going to explain you this analysis. For this, we go back to the original Hamiltonian. Now, the interaction strength, so the first line of the calculation, the Hubbard model, it assumed that the interaction is constant in momentum space. That meant that in real space, it is point-like. What that means is two particles can interact if they're sitting on top of each other. Now, you know Pauli's exclusion principle forbids that. So the only way these particles can sit on top of each other is if they have different quantum numbers. If they have same quantum numbers, they cannot be in the same spatial orbital, or they cannot interact at all. So the only way they can interact is if they have opposite spin. So the second term of this Hamiltonian is finite, or will give you some contribution only if you have opposite spin particles because of Pauli's exclusion principle. What that means is if you now polarize the system, that means all spins are same, either up or down. This would mean that these spins, the system, will have no interaction energy at all. So by polarizing the system, you're ensuring that the contribution from the second term of the Hamiltonian is minimized. So if interaction is very strong, if the interactions are strong and you have point-like interactions, the system minimizes its free energy by fully polarizing the electrons. Any questions? Okay, so next so this ends our discussion of ferromagnetism. Yes.
The line that you're putting there, like the straight line between the two graphs. No, in the graphs, is it gamma?
Yeah.
Okay.
This one?
Yeah.
Sorry, what was the question?
Is it gamma?
So this is Fermi energy.
Oh, okay.
So the information about gamma is in some sense buried in it. So this chemical potential, like it includes U and so on. So this is just a sketch. The main point is to calculate this spin densities. In general, you will have very complicated density of states, and you will have to calculate this area under the curve. So next what we want to discuss is superconductivity, which is, so this is one state that we usually encounter in condensed matter, and we've taken simple example to understand quantum theory of ferromagnetism. Next, we would like to understand superconductivity. So to motivate this, so far all these interactions, they were Coulomb interactions. And for electrons, this is repulsive. Electrons repel each other because of Coulomb interactions. In superconductivity, we'll include interactions between electrons which are attractive. These are not Coulomb interactions. These are interactions which are mediated by phonons. So phonons play a very important role in superconductivity. So next we have to discuss is phonons. Maybe an hour of the discussion of phonons may seem trivial, but nevertheless we'll go through it. We'll try to go over it very fast. But keep in mind that this is necessary, this is essential, and phonons are very important excitations in condensed matter. One example that we'll consider a lot in this, we'll talk about it a lot in this course, is in connection with superconductivity. Phonons play a very important role. So our goal, our long-term goal, which is over the course of next 2 or 3 lectures, is to have an interaction between electrons which is attractive. This would be different from Coulomb interactions. In Coulomb interactions, these are photons. So in here, this exchange of momentum is carried by phonons. So this is our goal. So to get there, we'll have to discuss phonons first. And another important thing about phonons is they were first used to explain specific heat of materials. So if you think about a classical system, say take a solid. Now this solid in 3 dimensions, it has 3 kinetic energy degrees of freedom, 3 potential energies degrees of freedom. So it has 6 degrees of freedom for each ion. So for each ion, you have 6 degrees of freedom. So if you calculate energy just from classical thermodynamics, use equipartition of energy. If you calculate energy of a crystal, this will be half. Let me use small kb for Boltzmann constant. So half kBt times total degrees of freedom. Total degrees of freedom is number of ions multiplied by 6. So you have 3 number of ions kBt. This is the total energy. So if I now calculate specific heat at constant volume, I will find that this is a constant. This is nothing but the classical law of Dulong and Petit that we learned in our elementary thermodynamics course. When we measure, if you go in a lab and measure specific heat as a function of temperature, so let me now plot CV divided by 3 N ions KB. So this is equal to 1. This is value 1. So this is what the classical law is. We go and measure this in the experiments. And what we find is that at low temperature, this is the experimental data. And what we will like to do is to explain this. And at very low temperatures, we should use quantum theory. The energy is quantized. You will try to explain the low temperature behavior of specific heat using quantum theory of phonons. After that, we'll move to superconductivity. And classically, we will argue that at low temperatures, all the degrees of freedom, they freeze out. And when they freeze out, the total number of degrees of freedom is actually 0. So at 0 temperature or close to it, you should expect a vanishing specific heat. Now, there are two models for this. One is Einstein model, one is Debye model. We'll say a few words about both of them. And towards the end of next lecture, for sure, we'll theoretically explain this behavior for specific heat. Any questions? So I hope I've convinced you that we should spend some time in learning about phonons. So we will start with something very simple. So what are phonons really? These are particles corresponding to vibrations of ions. So far, we considered ions in periodic lattice, but we ignored their kinetic energy. Sorry. Let's take one-dimensional lattice. So now we are going to include dynamics of the ions. If ions are stationary or at equilibrium, these dots represent the location of ions. At any instant of time, the ions will be displaced from their equilibrium position. So this is at equilibrium. Or this is at some instant. Now I'm denoting the location of ions by cross. So these dots, they represent the equilibrium position of ions, but these ions are vibrating around their equilibrium position. So at any instant of time, if you try to draw this picture, the ions that correspond to each side will be slightly displaced. We'll denote these locations of equilibrium positions as n times A, n plus 1A, n plus 2A, and so on. And the displacement of the ion at Na is denoted by U as a function of Na. Any questions? So next, what we are going to do is we are going to write down the interaction potential that represents interactions between the ions. So let's call this U again. U is sum over I and J not equal to I. V mod Ri minus Rj, where these Ri and Rjs are now coordinates for ions. So for this discussion of phonons, let's forget electrons altogether. So let's forget electrons altogether, only consider ions, and later on we'll add electrons and talk about electron-phonon interactions. So this is interaction potential for ions. We discussed in the first week that this interaction potential is minimized if the ions are the ions arrange themselves in a lattice. So next what we are going to do is we are going to write down the coordinate of ith ion as their position at equilibrium times some displacement so I can write down this quantity as where Rij is Ri minus Rj, or it is the separation between the equilibrium positions of ith and jth ions. And Uij is Ui minus Uj, where Ui and Uj are displacement of ith and jth ions. The reason I'm writing this in general form is because there is a problem either in the tutorial or in the homework, I think in the homework, where you will have a more complicated case, and this notation is useful to address that problem. In the lecture today, we are only going to consider one-dimensional lattice. What that means is, for the moment, these ions are only moving along x-axis. And in the homework problem, you will have a two-dimensional lattice and you would have much more complicated interaction strength. What we are going to assume is only nearest neighboring ions are interacting. And in the homework problem, you will go beyond nearest neighbor approximation. You will include next nearest neighbor interactions also. So let's simplify the calculation. We are going to assume that the ions are only moving along x-axis. It's a one-dimensional lattice. And they're only interacting with their nearest neighbors. So next what we can do is we can use Taylor expansion, and we'll expand this potential. And we'll write this as so assuming that the displacement around the equilibrium position of these ions is small, we will ignore all higher terms and keep only terms up to second order. Now, assuming that the ions have arranged themselves in positions so that at equilibrium they minimize the interaction potential. That means the first derivative is 0, second derivative is greater than 0. That means this term is evaluated at equilibrium positions must be 0. So this term will go away. This term must be greater than 0, and this can be used to define a variable we'll call capital K ij, and this will be related to spring constant. Any questions so far? Now, what about the first term? So the second term goes away, and we'll keep the third term. The first term is just a constant. We are interested in dynamics, so we are going to ignore the first term also. So what we are left with is U, and now I'm going to write down the expression for nearest neighbors, and because we have restricted ourselves to second order, I'm going to call this harmonic. So this is just a notation. This is also called harmonic approximation. So what I'm left with is that the interaction potential is now sum over n, u na minus u n plus 1a and we're going to assume that the lattice is isotropic and all Kij's are same. So next, what we are going to do is, in the second term, you can relabel n as n prime plus 1 and use periodic boundary conditions. That is u n plus 1a is same as u of A. And using this, you can show that the nearest neighbor interaction is simply k by 2 sum over n u n A minus u n plus 1A. Any questions? So next, we are just going to write down the Lagrangian, which is the kinetic energy minus, so you just have sum over n. So capital M denotes the mass of the ions. We assume it to be same. Now this looks very familiar. This is Lagrangian corresponding to a massive point mass attached to a spring. So if you write down the Euler-Lagrange equation of motion corresponding to this Lagrangian, you can derive that the equation of motion is m u double dot n A is minus k So this is the equation of motion that we would like to solve to understand the dynamics of the ions. What we are going to do is we are going to seek solutions that are of the form plane waves, which are basically plane waves and harmonic in time. So we seek solutions that are of the type e to the power I k Na minus omega t. So if you put this in the equation of motion, one thing, so this is just a substitution that we are going to do to solve this equation of motion. One thing you can see from this form is that if you increase k by 2 pi over a, here you just get a phase factor which is irrelevant. So u and a, if you translate by 2 pi over a, you get back the same solution. This is, of course, we know this is related by they're related by the reciprocal lattice vectors. So we are going to restrict ourselves to k values within the first Brillouin zone. And we know that if the translation, so we're going to restrict ourselves to this, and we are also going to impose periodic boundary conditions. So if you impose periodic boundary conditions, you have un plus 1a is equal to ua, and if you put that in this, you'll find that k, again, this is similar to what we did in the first week, k can take values 2 pi over capital N times a times some integer m. So we'll restrict k to the first Brillouin zone minus pi by a to pi by a. This corresponds to the small integer m from minus n by 2 to n by 2. So now if you put this in the equation of motion, you can see what you will get is minus m omega square So we find the solution that describes this dynamics. It's basically given by frequencies that are now functions of k. And if we plot these solutions, let's say we're plotting in the first Brillouin zone, we're plotting omega as a function of k. So these k values are discrete, and this comes from imposing the periodic boundary conditions. We're going to restrict it in the first Brillouin zone, so pi by a to minus pi by a. And the solution is mod sine ka looks something like this, where this value here is 4k over m. So what we did in the last 10-15 minutes is same as finding normal modes of the system that you've done in classical mechanics. The key point here is to remember the phononic dispersion relation is very different from electronic one. So in general, if you're going to calculate density of states and many other properties corresponding to this dispersion, you will get very different answers. So for this simple case, you have this dispersion. What happens in the limit k going to 0? In the limit small k, you can show that this can be replaced by mod ka by 2, small k. So omega is linearly dependent on k, and this corresponds to sound waves. So in general, you have linear dispersion for light waves or sound waves. So this is the reason we are going to call these type of solutions that go linearly to 0 with k for small k as acoustic phonons. So this branch is going to be called acoustic, or this solution, this band is going to be called as acoustic phonons. You can think of this whole system as ions connected by some springs. Any questions so far? Yes.
Doesn't this look like the dispersion of light?
The linear one?
Yeah.
Yes, it does.
So
And
why isn't this the optical dispersion?
so when we put in numbers, this corresponds to motion of ions, and it will be orders of magnitude smaller than speed of light.
So it refers to like what can excite them.
Yeah. If you're at the Crompton scale, then it will correspond to this. But we are really talking about ions in the solid. And there is a optical branch for phonons, and that is we're going to discuss next, but that has nothing to do with the linear dispersion. So this we can understand in terms of ions connected to springs. We can consider a somewhat more complicated system where you have two types of ions, similar to what you did in the tutorial. So we have two types of ions. Let's say this cross and so on. Now the location is again NA, N plus 1A, N plus 2A, and so on. This distance is given by D. Now you would see, if you go through the same analysis, I'm not going to bore you with that calculation. So what we'll find is that this second derivative, now we'll have to evaluate at two positions. So at equilibrium, there are two distances. One is the small d and one is A minus d. So you will have two types of springs, and we are going to call them K and G. So K spring, which is evaluated, which is the spring constant corresponding to distance between the ions, that is d. Let's denote it by this, and the G spring is denoted like this. So what you really have is this spring and this. And so on. Now we all can solve this problem and calculate normal modes of this system. Now we have two types of displacements. We are going to call them U1, which is the displacement of the ion denoted by cross. Let's substitute this to be epsilon 1. So now when we write down the equations, first we write down the Lagrangian and then write down the Euler-Lagrange equations of motion. Now we have two types of ions, cross and plus type. So the equations involve two variables, U1 and U2. We seek solutions of this type. So we substitute for U1 and U2 this function. And when we put this back, we find out that the final solution we'll get is omega square equal to K plus G divided by M plus minus 1 over M square root K square plus G square plus 2 KG cosine KA. And epsilon 2 over epsilon 1 So what we have done here is we now consider a system where we have two ions per lattice side. We have two types of ion. We write down the Lagrangian, solve the equations of motion, and find that now we have two solutions for each K value. Each small K value, we have two solutions. Let's plot them. when you plot them, these solutions would look like, again, we plot them in the first Brillouin zone. One branch looks very similar to what we had before. And the other branch looks like this. So go through the calculation. They're done in detail in the notes. And this is what you will find. So this is omega as a function of k. How many values of small k are there? There are total n, capital N values of small k, which corresponds to the number of ions. And that we can see when we impose the periodic boundary conditions there. So there are capital N discrete values from minus pi by a to pi by a, which are labeled by the small m values from minus n by 2 to n by 2. And for each of these discrete values, you have two types of solutions. This, the lower branch, is similar to what you had when you only have one ion per site. The complication that this other ion brings is it gives you another branch of the solution, which is this branch. Now, if I draw, you asked about the light mode. If I draw on this same curve, speed of light, it will be very difficult to draw. The slope is so large that I'll have to draw a line like this. So speed of light is very large compared to the speed of sound. But if I try to draw this, you can see that there is no way this curve is going to intersect with the lower branch, but this curve will intersect with the upper branch. So we think of this upper branch as optical phonons. So this lower branch is called acoustic phonons. And this upper branch is called optical phonons. The reason they're called optical phonons is because these phonons, which are vibrations of the ions, these modes you can excite by light. Any questions? Yes.
How does this excitation happen when a photon and quicker?
So one way to see this is to look at this epsilon 2 over epsilon 1. So if we look at this in the limit k going to 0, so at this point, we'll find that this simply goes to minus n plus 1. Plus 1 corresponds to the acoustic case, which corresponds to propagation of sound, where this cross and plus, all these ions move. So what is epsilon? So they are both basically have the same sign. What that means is that the displacement of both of these ions are in phase. So either both of them move right or both of them move left. Minus 1 corresponds to optical branch. Now in this case, you will have if one ion moves left, one ion moves right. If the cross, they're basically out of phase. So either they will be moving opposite like this or like this. Now, in this case, you can show that this gives rise to a finite dipole moment. And this electric dipole moment, so these are same charges, assume that ions. In this case, you do not have a finite electric dipole moment, and therefore they don't interact with light. And here you do have a finite dipole moment, so they interact with light, and you can excite them using light. Also, if you draw the curve, you can see it only intersects with the speed of light. If you draw the dispersion for light modes, it's going to be a very sharp, it's going to be something like this. And this will be the mode that will get excited by light. Any other questions? So go through the details of this calculation. It's really a trivial calculation, but just to convince yourself that we can calculate, in principle, we can use whatever we have learned so far about periodic systems to calculate dispersion relation for ions. And in general, we get two branches, acoustic phonons and optical phonons. So what we are going to do tomorrow is we are going to quantize this theory. So far, we have a theory of phonons, which is classical. We're going to quantize it and then use this quantum theory of phonons to show that the specific heat of a solid goes to zero as we measure in experiment. Or what we find is that the specific heat goes to zero as T cube, where T is temperature. Thank you.